Good morning, everybody. So this is today the last but 1 week of the lecture, but the last week where there will be course material. Next week it will be something a bit different, just a wrap up. I'll summarize on a high level what we've done during the entire lecture, so nothing new. I hope to be able to also throw in some quiz game also on the lecture material with multiple choice questions, which is also a way of preparing you for the exam. So please come next week. The more you are, and the more interesting playing this game will be. So let me start with today's material. In the book, there's a lot. The book is much bigger than the lecture we are doing. And roughly, in the book, chapters 1 to 8 corresponds to what is typically taught at the undergraduate level in information retrieval. I've already done chapters 1 to 7, which was the meat, the algorithms for information retrieval. Chapter 8, I left for today. And in the last 2 weeks, we even looked into advanced material that typically is almost on a master's level. It is actually on a master's level with probabilistic information retrieval, language models. But I think it's still interesting to look at it so that you know exactly what's going on in more fancy algorithms. So of course this is also exam material, but I'll be a bit, it will be less stuff than for chapters 1 to 8, so no worries about that. So this is the last missing core parts with the evaluation of an information retrieval system. I like to wrap things up a little bit. So just so you remember, in the first weeks of the lecture, we looked into Boolean retrieval. In Boolean retrieval, either we return a document or we don't return a document, and that's it. So what you have is a set of documents as an output, and we had this kind of query with and, not, or, and so on. And the abstraction for this was the set of words, meaning that each document here is just a set of words. We don't care about the order of the words. We don't care about the number of occurrences. What we end up with is a vector of Booleans. And vectors of Booleans we saw plenty in this lecture. Even, again, in the probabilistic information retrieval, we had even random variables on vectors of Booleans. This now you know by heart. I mean, I spent a lot of time in the first week on the standard inverted index, and just for the reason that it's used everywhere, not necessarily as is, so we improved it a little bit to implement other features, but this is the central structure of information retrieval. And the way we look up on the left here it's just a flat list of terms, but the way that this flat list of terms is organized is typically with a search structure, like hash tables and trees, B plus trees. And then we looked into a second kind of retrieval, which is ranked retrieval, where what you want is a ranked subset of documents. You no longer just want a set, an order, but really a ranked subset of documents. But we no longer do Boolean queries. All we do here is the good old Google queries that you type in natural text in the browser. And of course, for this, we changed the abstraction. We no longer have a set of words, we have a bag of words with vectors of numbers. Then we came up with a vector space model, looking at documents as vectors. Then I told you something. It's an entire advanced chapter on the book that is not in the course material, but you should still know that when we do this kind of system, we want to return relevant documents. And one way to come up with relevance is to just ask the user, do you think that this document was relevant? And so this whole thing about relevance feedback is that you keep outputting results to the user and ask them feedback about what in which you return to them was relevant. This is one of the ways that we can then use it in a probabilistic setting when we estimate the probability that a document would be relevant based on the facts, based on the terms that the document contains and the query. And this is one way of having some kind of, I'm using a lot of precautions here, a training set or some kind of data that you base your calculations on. And then this probabilistic information retrieval that we spent 2 weeks on was more or less that was more or less the conclusion of it. So do you remember just how we arrived to this? So if I come back here, what did we actually start with for probabilistic information retrieval? What rule did we use and write down in order to start deriving some fancy formula? So remember that in probabilistic information retrieval, we rank the documents by our estimate of how relevant it is, based on the query and the content of the document. And so we start with this probability, and then we use one of these in order to start the calculations, and then I spent probably 2 hours deriving everything in there. So I have 9 votes. Can you raise your hand, please, if you need more time? Yeah, I'm rating a bit more. Let me see. Very good. And you will even spend today's exercise session discussing the Bayes rule. Based on, do you know the Monty Hall problem? The 3 doors? Okay, well you will think about that with the Bayesian rule. It's just the same thing we have been doing with relevance and documents, but it's just a different setting, but the idea of Bayes rules is exactly the same. Oh, by the way, just checking, one of these formulas, if you use something like that, I'm going to be very upset. Which one it is? Which one is it? Welcome back. So let's continue. There's one more thing I wanted to say here, just to test, prepare us for the exam to think about that. Quick question. We had these 7 documents. We built this language model. For these documents, were we using the list of words, set of words, or bag of words models? Which one of these? The way we built that. Did we care about the order? Did we care about the number of occurrences? List, set of bag, yes? Bag of words, exactly. That was the bag of words. But now, the query that we generated, was the query order sensitive? Was it a list of words? Was it a bag of words or a set of words? When I told you it's a probability of 964, is it the probability of generating that exact list, or the bag, or the set? Yes? That's exactly what I'm coming at, actually. So there is a little thing to say here. So when we computed that probability, it was actually order sensitive. You will see that it's actually fine that we did that. But to be very precise, when we multiplied these 3 things, that was really the probability that foo gets generated first, and then bar, and then foo. So this is the probability of generating the query as a list of words, right? It's exactly that order, yes? That's a trick. So I'm trying to figure out how to answer it. The way you formulated this makes it tricky. Let's take an example with coins, heads or tails. It's exactly the same thing. I'm changing the blackboard just to separate things. So I'm throwing a coin twice. So either I have head, tails, tails head, or tail, right? If it's uniform, that's each 1/4, right? And the way I get the 1/4 is just there is 1/2 of getting h times 1/2 of getting it, right? So it's 1/2 times 1/2. We do it every time. Is it list or bag? If you take the example here, I have 1 chance in 4 of generating ht. Is it order sensitive or not? in that case it is. It's really 1/4 of HT and 1/4 of TH, right? The ordering matters here. If you want to get rid of the order, you need to group them. You need to basically say it's the sum of these two probabilities, then it's the bag of words. Then it's 1/2. What do you recognize here? 1, 2, 1. It's exactly this in combinatorics, right? Binomial distribution. As it turns out here, we don't have 2, we have 3. So the distribution here, the multipliers, would be more like 1, 3, 3, 1. Because this would be for everything foo, 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 bar, bar, bar. Here it's 2 times foo, here it's 1 time foo, right? So we need to multiply by 3 because this probability here. Because foo bar foo is one possible ordering. It could have been bar foo foo or foo foo bar. There's 3 combinations. So if you want to convert this to a bag of words probability distribution, you need to multiply by 3, right? This is very important. And actually, so if you have the list, you're basically too precise. You are giving too many details because you actually even describe the order. And if you consider how many possible bag of word queries are there with 3 words, just foo and bar, there's just 4, right? Either you have the bag foo foo foo, or you have the bag foo foo bar, or you have foo bar bar, or you have bar bar bar, right? If the order is irrelevant. Now we already calculated for this bag, it's basically 9 divided by 64 times 3. So it's basically 27 by 64, right? Now, if I did everything consistently, this plus this plus this plus this should sum to 1, right? It's a very good exercise to actually do it. Because here, foo, 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 I have, it's this column, 3/4 of chance every time. So it's 3 to the power of 3 divided by 64. So here it's 27 by 64 multiplied by 1, because here I don't have any order, right? So it's exactly 27 by 64 here. If we do the same here, foo, it's 3/4 for document 6, 3/4, 1/4. So here, what probability do I have? Yeah, with the order that matters, it's 3 by 64. How many possible orderings do I have? 3. Again, it's the binomial distribution, 1, 3, 3, 2, right? It's this nk when you have, when you do this. These are the coefficients by which we multiply, which is 1, 3, 3, 1. So here I multiply by 3, and I get 9 in 64 for getting this back here with the order irrelevance. And here, the probability of it having bar, 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 it's 1/4 for bar every time, so it's 1 in 64. Times what? Times this, right? So, times 1. So these are the 4 possible bags of words. If I have 3 terms in my query, what is the sum of these 4 probabilities? 1. So you see everything's consistent. So what you see, the only thing that I'm making you aware of here, we should need to multiply by 3, but we didn't need to in that case. Why? Because it's everything multiplied by 3, it's a constant. So it doesn't change the ranking. I just want to be precise here. If you want really to be very precise and have bags of words, you do need to correct the probability with this to correct the ordering. Right? It's even in the book. There is this super complicated formula that they even give for the general case, but here it's a more simpler case. Okay, but I'm closing the parenthesis, just closing on language models. Very good. So I promised you something. We saw precision and recall. What is the formula for the precision? Again, how do I define precision here? Yes? So relevant, exactly, relevant positives over the sum of 2, right? And the recall? True relevance, exactly, that's recall. So basically we have, I can't believe we actually need chairs in this lecture hall. So, here on the first line, we have precision. here we have recall. So we have two other possibilities that we didn't do. There is this here, the bottom row, and there is this here. It so happens that specificity is exactly this. So it's exactly the same thing as recall. We basically look at the number of true negatives, so the non-relevant documents we didn't return, divided by the total of non-relevant documents, that's specificity. What's the specificity here? Everybody? 50%. 50%. That's 100%. We only have correct results. We do not return non-relevant documents. Here it's 0%. This is the nightmare. You basically return all non-relevant documents which you shouldn't have done in the first place. And here another example, it's 67%. There's 2/3 correct, 1/3 incorrect. This is specificity. Could you define specificity in terms of recall? Connect the two? How could you actually argue that specificity is the same thing as recall? With a little mental exercise. Specificity is actually the same thing as recall. But you need to say how it is the same thing. Yes?
I would say it's inverse proportional because we return more. Well, when we recall, we have a very high recall if we just return everything. But then we have a low specificity.
Mm-hmm.
If we return nothing, we have high specificity but low recall. So it's correlated inversion.
Okay, so that's a conjecture. You're basically conjecturing that if you have high recall, you have low specificity and vice versa. So all I need is a counterexample. It's much easier to actually prove a conjecture false than a conjecture true because false, just a counterexample. All I need to do is draw something actually. I can give you something both high recall and high specificity. Just plenty of documents here, plenty here, nothing here, nothing here. It's high recall, it's high specificity.
Yeah,
it's hard to achieve, I agree. Yeah. But theoretically, you can have that. So I agree that in practice, you are absolutely correct. And we will actually even have curves that plot that. At the end of the lecture, you will even see curves. So you're absolutely right in practice, this is true. The meaning of my question was more to give a mental exercise to actually transform the problem into another one such that specificity can be defined in terms of recall. Here's how. So in terms of machine learning, imagine just in a machine learning setting, you have several kinds of problems. What is the general category of machine learning problem that we are solving in information retrieval, in Boolean retrieval? Right here. What is this? Is this a regression? What is this? We're basically returning some documents, not returning others. So this is a classification problem, right? What we are doing here, so in machine learning, you have two kinds, very roughly speaking. You can have regressions, where you try to actually have real numbers as in outputs or whatever numbers you want. And you have classification. Classification is just to label. So I give you 1 million of pictures, and then you put stamps like this is a cat, this is a dog. This is a classification problem. And believe me, people are actually doing that. There's actually researchers stamping cats and dogs, because it's one of the easiest use cases that you can find for a classification problem. So this information retrieval, another way to look at it from a machine learning perspective, information retrieval is a classification problem. We don't actually solve it with machine learning. We have our own tools with the indices and so on. But this is a classification problem. I classify my document as return, non-return. It is an attempt at saying what's relevant and not. But of course, we have these errors, false positives, false negatives. But when I say we classify documents, I'm making it symmetric. Because in information retrieval, when you say we return documents, we don't return documents, we have an asymmetry because we're interested in the returned documents, right? But if you consider it a classification problem, it's fully symmetric. You have two labels, A and B. So the documents you return, you label them as A. The documents you don't, you label them as B. But now imagine that you swap it. You have category A and B, return, not return. swap it. Consider that now you return the ones you didn't return before and vice versa. So you return category B and not A. Then do you agree that specificity in the first that you returned the documents called A is the same as recall if instead you consider that what you return are the documents in category B? Who agrees with that? A lot of you, okay. Because that's exactly what's going on in here. If you, So in this setting, you really realize recall is right here. It's this divided by this, the sum of this. Specificity is this divided by the sum of this. So you can actually see the symmetry here between relevance and non-relevance, right? If you swap it, then you basically redefine them in a different way. Okay. You would have to swap both the columns and the rows, by the way, to really be consistent. Okay, so this is, I'm telling you that as a way to remember things, in order to remember things that really it's specificity on the right, recall on the left, and precision is just different. By the way, we don't have any name for the bottom row. We could imagine one, but there is none. So specificity, I already told you this is here. Yeah. Well, I have another one, and that's accuracy. It's the fourth one. Accuracy is this. Accuracy is, now you take even the bigger picture, accuracy is just what's correct, what's not correct. It's symmetric. So what's correct is the true positives, this is correct. The true negatives, this is correct. This is wrong, you did not return documents you should have. This is wrong, you returned documents you should not have, right? So accuracy is everything's correct divided by everything that's incorrect, right? And actually, it's often the first idea that you would have to evaluate an information retrieval system. Accuracy. What's the amount of correctness that I have? This is a very bad measure for information retrieval. So I'm giving you this definition, but it's not used. And actually, it's quite easy to say why. Exercise, what's the accuracy here? Hope I got that right. Correct divided by total. Anybody? Any number? In percent? Yes? 2/3. Yes, 2/3. Yeah, exactly. It's the green divided by everything. This is 100%. This is your dream search engine. Your dream search engine returns the relevant documents and doesn't return the non-relevant documents, right? Accuracy 100%. This is 0%. Right, this is not good at all. So now, I have to tell you why accuracy is not good. Accuracy is not good because you can hack it. How can you hack accuracy? Imagine you're Google. You only look at the first 10 results. How can you hack your system in such a way that you get a very high accuracy with very little effort and even implementation effort? It's very simple. Yes?
You only return documents that you're actually very sure that they are relevant. Like if you decide to return 10 relevant and 10 negatives, not relevant systems to the accuracy, we just return the top of documents at the bottom, 10 documents, and then you reach it. I thought interesting is this. Our documents, they are just near the cutoff value, like for being relevant or irrelevant.
Yeah. So I think you're correct. This would be a way of making it high. But imagine you're lazy, because there's effort in what you say. You would actually have to try to find relevant documents and so on, right, to be sure of them. Even with less effort, very lazy, what could you do to get it almost for free? Yes? Exactly. If you don't return anything, it's just statistics basically, because imagine there's billions of web pages. If you have a research, in general, it's very rare that all web pages are relevant. In practice, what happens is that most of the web pages are irrelevant, and the web pages you're interested in are actually much less. So if you don't return anything, then accuracy is this divided by the sum. And actually, in practice, it can very easily be 99% just by not doing anything, just by not returning anything. So I hope that this shows to you why that's a very bad idea to use just accuracy. You can basically cheat the system. You can also hack recall. You know how? It's also very easy. How can I get 100% recall? Without being lazy, yes? Exactly. If you return everything, then that's it. You basically, I didn't draw the right side, right? There would be stuff, but the recall is only here. If you return everything, you have 100% recall, right? So recall alone is not enough, right? Recall is basically 100% recall in practice is when Rachel Zane erupts into Jessica Pearson's office where she finds the one documents that they needed to solve the case, right? This is really, she looked at absolutely everything. So her return results were complete. Who got the reference? Some of you, okay. So this is a recall of 100%. So now if we merge precision and recall, that's actually what we did in practice. We actually have some mixture. The first idea, we could take the mean. We compute the precision, we compute the recall, and we take the mean. Okay? The problem with that, with just the mean, is that even if you have very bad recall or very bad precision, you still can get a mean of 50%. So that's not very, very good. So the arithmetic mean is not very interesting. What kind of mean could you use instead? Geometric, harmonic, there's plenty of different means, right? And actually the harmonic mean is perfect right here. Because the harmonic mean will, if the precision is very bad or the recall is very bad, then it will also be bad. So this is why this is the harmonic mean. You know the harmonic mean, right? It's just the inverse of the mean of the inverses. This can be simplified to this. If you know about electronics, it's very similar when you compute resistances in parallel. Who remembers that? That's how I remember this formula, actually. I remember in electronics, that's how you compute. Anyway, this is just a special case of weighting because we actually can change the weight alpha. You can weight the precision and the recall. And depending on the value of alpha, you can say, I'm more interested in precision, I'm more interested in recall. So if alpha equals 0, you are interested in, plug it into the formula. If alpha equals 0, yeah, that's the recall. And if alpha equals 1, it's the precision. So then you can weigh in between, anywhere you want, the slider. This is pure recall, this is pure precision, and then you weigh. And you can adjust alpha depending on your needs. Again, there is no universal solution, depends on your use case, right? Okay, this was for Boolean retrieval. Boolean retrieval is super easy because all you need to do is do this matrix. You have these 4 cells, you have a number in each cell, just the count, and then you do integer division. That's all you do. That's all you need to do for precision and recall. This is super easy. But this works because Boolean retrieval is a classification problem. All we want to do is label the documents as returned, not returned. That's a classification problem. So it's sets everywhere. But in ranked retrieval, it's more complicated because in ranked retrieval, we actually order the documents, right? So we need to take into account this scoring, the ordering of documents. And there is something else in the behavior of the user in an engine. You do a search, you look at the first 10. If you don't find anything, you may click on next, look at the next 10, and so on and so on. So when you use a ranked engine, you actually browse down in the ranking, right, until you find something. What's interesting is that I think that research shows that nobody really goes after 3 pages. I think most people already stay on the first page and maybe 2 more pages, but then being ranked after page 3 is very bad. So how do you think we could find a way to using precision and recall, but on ranked retrieval? Do you have any idea? We need sets, basically. In order to define precision and recall, we need to fix a set. How can we do that? Imagine, very simple example, somebody does a Google query, and then you have the first page, 10 documents. Who agrees you can compute precision on that and recall? You can, right? Because if you consider that the page, the first 10 are a set, as if you had a Boolean retrieval system and you just return the first 10 and nothing else, if you fix the value of k, of the top k documents, then you can define precision and recall. That means that for any k, for the top k documents, you can compute precision and recall. Then basically, es liegt auf der Hand, if you vary the value of k, you can plot something. You compute it for k equals 1, compute it for k equals 2, 3, 4, 5, and so on. And if you even have infinite power until you return the entire web. I don't actually if it works with Google, if you can actually get, in theory, the entire web returned in a query. It would be a nice experiment to test. So let's try that. So of course, I told you we vary k, so you could have thought we put k on the x-axis and then precision and recall together. Actually, that's not how we do that. So we do vary k, but we still plot precision against recall. It's called the parametric curve in mathematics, when you vary some parameter, but not on the x-axis, but just along the curve. Relativity physicists love that, when you have this intrinsic time when you... Anyway, I don't want to start talking about physics. So we have the precision against the recall. So let's do it together. I have somebody searching the web, looks at the top 1 document. The top 1 document may be relevant or maybe not relevant. So let's look at the two cases. If it's relevant, the first return result of Google is relevant. What points do we get here? Where do you put the points? What's the precision and the recall for just this? Anybody? Yes?
Well, if we finish our search afterwards, it's 100% each. I mean, if this is the document, the single document that the user was looking for, then we have 100% precision because we return the single document that the user was looking for, and we have 100% recall because it returned exactly the document the user was looking for and nothing else. So
So you give two answers. So I'm going to take each answer in turn to be very precise. So you said 100% precision, this is correct always. Because it's just green, everything you return is precise. So this is 100% always. Then you gave a second answer, you said 100% recall, but you made an assumption for that. When you told me 100% recall, you said if this is the only document that I need and there is nothing else. And yes, in some cases you may have 100% recall. But in some other cases, it's possible that not. Maybe there's 1,000 documents or 1,000,000 documents. In order to plot the curve, I'm going to assume maybe there's, let's say, 10 or 20 relevant documents, maybe 1,000, 1,000,000. It's just to draw my curve. But you're absolutely correct. It may be that you already have 100% recall already there. But then it's a special case. Yes?
But especially like if we take examples who probably have this case quite often because often people search in Google which something they could easily type in the URL, which helps Google to exactly identify the page they want to land on. So
You're absolutely correct. So yes, there is a very famous, a very common use case that there is just one relevant page. I realize, I think I don't know if people still do it today, but 10 years ago, some people were actually typing their URLs into Google and then clicking. It still happens. Okay, well, this is very interesting. Anyway, in this case, yes, you have just one relevant document. That's it. It's 100%. It's the first one. Mathematically, theoretically, independently of practice, I would like you to think that of a special case. And then we are going to get a very special curve. We can come back on that later. Right here, I'm trying to give you the very general look of the curve, assuming there may be more relevant documents. But this is very, what you're saying is relevant. This is absolutely true. And you need to think about the way that the users use stuff. So this is where it is. 100% precision and maybe very low recall, because you're just at the start. You only look at one document, maybe over thousands. What if it were not relevant? Then you have 0% precision and still 0% recall. So it's one of these. But let's assume it was relevant. I get a second document. Maybe it's relevant. So what will happen is the precision is still 100%, but my recall is increasing. So where's my new dot? It is right here. Or maybe it was irrelevant. Then the recall would remain the same, but you would be halfway here because you are at 100% precision. So you see, two things can happen. Either it goes down if it was not relevant, or it goes to the right. So let's continue. Not relevant goes down, 2/3 of precision. The recall remains the same. Then maybe another non-relevant. Now we are at 50% precision. Now a relevant document. So you need to think at what happens here. Precision improves again, because now we jumped from 50% to 60%, right? So here we have better precision, and we improve the recall. So whenever you return a relevant document, you're both improving precision and recall. This is very good. When you return an irrelevant document, you just go down, because you're less good on precision without improvement on recall. And if I continue, that's exactly what happens. Non-relevant goes down, relevant goes up. Oh, a lot of relevant documents here. Now, irrelevant goes down, relevant, just a batch of them. So this is what you get. And then at some point, you get some curve like this. This is exactly what it looks like in the general case, right? Of course, in the case that you already have a 100% recall, there is only one point in your documents. You know, it's just that point right here, and you're done, right, in the very special case. There is one more thing we do with that curve. We actually smooth it a little bit, because this doesn't look very good. So what we do is that we add these little, we take the max. So whenever it goes down and back up, we actually use this straight line, horizontal line in the middle. The idea is that it's based on behavior of users. Typically, when a user browses Google or browses search results, when they have irrelevant document, they keep looking down, and they stop at a relevant document. So it means that the points that you actually are is more like here, 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 but the users will not really stay at these points, most of the time, of course, not always. So what you get is that curve, and that's it, precision versus recall, right? And the curve typically goes down like that. So you can see the compromise here. If you have more recall, you have to give up on precision most of the time. There is this way, it's very common to actually plot the curve on only 11 points every 10% of recall. So you look for, as soon as you have 10% of the documents you wanted, you plot the precision, then 20% and so on, until you get 100%. Very often, you're actually very low on precision when you're out there, right? It's very hard to actually not have a curve like that. So now, if you have an absolutely awesome search engine, what will it look like? Do I have a question about that? Let me check. Oh. I think ranked retrieval is this. I'm not sure I do. Yeah. So what would an ideal curve, if you have the most fabulous search engine you can ever imagine, only returns relevant results, never returns non-relevant results? Can you tell me? Yes? In the upper right corner, right? And the entire curve would look like? Yeah, that's it. That's the curve. So this is an awesome search engine. This is an awful search engine, right? You basically keep returning documents that are irrelevant. Once in a while, you return a relevant one, but it's just lost in the irrelevant documents. That's one curve. It's the precision against recall. Who gets this? Precision against recall? Very good. So now, this is actually the last part for evaluation. Let's see if we have time for PageRank after that. Recall versus sensitivity. This needs a bit more thought to actually understand what's going on here. I should have said versus specificity, by the way. I keep confusing sensitivity and specificity. So the first thing I want to say is sensitivity is just recall. That's the same thing, it's just that the people that do these curves, instead of saying recall, they say sensitivity. I will explain to you why. Specificity is, remember, it's the same thing as recall. So recall can be seen as how many false negatives do you have? You're looking at, do you actually forget to return relevant documents? Specificity is the same thing for false positive. You're more worried about if you return too many documents. That's the specificity. So if you have bad specificity, it's a lot of false positives. If you have bad recall, it's a lot of false negatives. ROC means, what does it mean? It means receiver operational characteristics. It may look like it doesn't mean anything. It's actually because of a different context. And the way that I actually will explain it to you is by taking an analogy with something else. But you will see that it's the same thing with information retrieval. Recall that information retrieval is a classification problem. You want to know if you should return or not a document. But let me do something else. Imagine you are on a beach and you're trying to find metal or gold or whatever. There is gold buried. And you have this, let's say this is a magic stick, it's a metal detector, and I can just walk on the beach and I can try to find it. If it beeps, then I found gold, right? It's a classification problem. I'm classifying the spots on the beach. Is there gold, is there not gold? Of course, I would be very happy if it beeps every time there is gold and if it never beeps when there is no gold, right? This is my ideal setting. But now, imagine that I have one feature on this. It's a fancy metal detector. It was very expensive, and I have this little feature here. I have a knob that I can turn. This knob is the sensitivity of the detector. Will it be extremely sensitive to metal, or will it be not sensitive at all? So let's start by having the knob on not sensitive at all. What will happen? It will never beep ever. You will basically walk on the beach. It will never beep. So for specificity, it's great. You don't have any false positives. You're very happy about that. So you have very good specificity. You're on the left one. One main specificity is actually there. So that's it. But the problem is that the recall, the sensitivity is not so good. You did it on purpose. You set it on 0. So of course it never ever beeps. But now let's turn the knob a little bit. You make it slightly more sensitive. So now it will start beeping when there is, like, let's say, a large quantity of gold, or it's very easy to detect. So it will start beeping once in a while, and then you have a bit more recall. You will find a bit of gold, still not perfect. You didn't turn the knob too much, so it will only detect the obvious spots where there is gold. And maybe because you're very careful, you just turn the knob a little bit, you don't get too many false positives either. So you start detecting gold, but it only beeps when there is gold. You are so not sensitive and picky that you will really only beep if you're sure that there is gold. So what happens on this curve? Oh, now the chair is blocking my way. If I am on that graph, I'm on very low sensitivity, so I'm here. And because I'm very sensitive, I don't have too many false positives, so I'm here. So if I start turning the knob to be more sensitive, I will go a bit up like that. I start returning true positives, detecting gold, and I don't beep for false alarms too much. So it goes up like that. But imagine that you actually find it pretty cool that it starts detecting gold, and you say, okay, why don't I turn the knob a little bit more? Why don't I even make it more sensitive? Then I have plenty of gold. What will start happening? It will at some point become so sensitive that it will just keep beeping everywhere. So yes, it's more sensitive, you have more recall, you will find all the gold everywhere on the beach, but since it beeps all the time, you're unable to tell the difference, basically. So what happens if you actually push sensitivity too much is that you start losing specificity, and the curve starts going like this, right? And this is called an ROC curve. And the reason it's called receiver operating characteristics, if you think of that metal detector, the metal detector is a receiver. So it comes a little bit from this area, this kind of curves. But now let's get back to information retrieval. What you're looking at is actually the sensitivity of your search engine. How sensitive is the search engine to returning results, right? And it's exactly, think of the search engine as a metal detector and gold as the relevant documents. Then what happens is exactly this. You basically plot. It's no longer precision recall. Now it's recall and specificity, 1 minus specificity. And exactly that happens. And now you know why the curve looks like that. If you think of the metal detector, it's exactly the idea that if you're a bit sensitive, that's fine. And if you push sensitivity too much, then suddenly you start having false positives. Okay? So what does the ideal ROC curve look like? Yes? Yeah. Oh, I have a few more slides. Yes, you're absolutely right. I will show that it's in a few slides. Thank you. That's the correct answer. So just to tell you, before we go there, Here, it means when there's high recall, we don't have so many false negatives. And here we have lots of false negatives. It's when it's so sensitive, it never ever beeps. Here we have few false positives, so it will never have false alarms. But here, if you push it too much on sensitivity, it keeps beeping all the time. So this is it. And this is now how you get your ideal curve, because we love green here. We love the not too many false positives, not too many false negatives. So this is what we love, the sweet spot here. This is what we don't like. So this is pretty good. This is fine. And this is here the curve. I'm not sure if you see it. This goes up all the way here. Imagine that you have such an awesome and expensive metal detector that you can push the knob to almost its maximum, and it will still only beep when there is gold, and it finds them all. This is an awesome search engine. And then, just for correctness, that technically you don't have to have the horizontal curve, but imagine you're not absolutely completely perfect, then you still have at some point that if you make it completely sensitive, you return everything. So you still have that loss of specificity here. What do you think is an awful search engine? You would think that, right? Yes, you would think that this is an awful search engine. Yes?
No, because this we could just reword the
Yeah.
results and we would have perfect. So this is the best. The worst we can get is like 45-degree angles straight line.
Exactly. That's exactly it. So I even prepared a question and everything, but since you figured out, you just saved me 5 minutes. So that's absolutely perfect. You're absolutely correct. If you did have a metal detector that is like that, I want it. Because indeed, you only need to revert when it doesn't beep, you just revert the results. And that's it. So it's actually pretty good. I'm not sure if it's already the bachelors, who took the cryptography lecture by Uli Maurer? Some of you, right? So I'm not sure if it's only in this first lecture, but do you remember these indistinguishability games? Yes? Oh, it may be a master's course. So just in case you visit the course, I'm just in advance telling you the parallel. In this course, you play these games to distinguish between systems. You have your ideal system, the perfect encryption, the perfect signature scheme, and so on, and you have your not ideal system, and then you play a game in order to distinguish them, and basically you're trying to have as much success as you want. But imagine that you have somebody who's capable of predicting, distinguishing the two, but he's always wrong in classifying. All you need to do is just turn the answer, right? So the real worst case is 50-50. It's not actually 0 or 100, right? So the worst case is 50-50, because otherwise you can, yeah. I mean, if you have a metal detector that always beeps when there is no gold and never beeps when there is gold, it's obvious that it's actually very useful. So this is it. So now, this is the really awful search engine, because here it's really a mess. You don't have any information, it just beeps randomly. So this is it. So that's it for the evaluation. That was chapter 8, not all of it. It's only the first 4 sections of chapter 8, so you don't need to read everything. So now you have basically everything that are like the undergraduate basics of information retrieval, chapters 1 to 8, and we even looked into probabilistic models, language models, chapter 11 and 12. So that's pretty good. I'll save PageRank for next week because that's kind of an extra. It's like, it's actually fun, PageRank, so maybe I can keep it for the last lecture. Today, in the exercise session, you will look at the Monty Hall problem with the 3 doors and the TV game. I will also tell you about the exam, by the way, next week. Maybe I can say actually a few words already. So there is all the exams from the information retrieval lecture. Just, you can use it, you can look at these exams. I will actually figure out if I can share these exams. Keep in mind that this was a master's lecture. It means that there was more material, it was on a master's level, it was more complicated. So what I will try to do is maybe show you the last exam that there was 2 years ago and tell you exactly what you should ignore in that exam. But some part of the exam may actually make sense and prepare you well. So there are still parts of this exam that are good for you. The exam will be a lot multiple choice, maybe very small open questions, but open multiple choice as much as I can. No pressure. I think I scheduled 2 hours and a half, but again, it's only for you to not have pressure because the exam will actually be designed for more like an hour and a half. But I will tell you more next week about that. You know that I remember that there was a lecture where the lecturer actually gave unlimited time. You could basically stay for as long as you wanted. I think that was a semester exam. But anyway, it's just to say that pressure doesn't help, so the less pressure you have, the more you can concentrate and pick the answers. So, how much of today's lecture did you understand? Precision recall specificity, the precision recall curve, how we do it in ranked retrieval, the ROC curve with this metal detector analogy. That looks good. Okay. So we'll have next week the lecture, but really it's just the last week, very general. I'll try to organize this game. Hopefully I can come up with interesting questions. And of course, these questions can also help you for the exam, right? Because it's going to be multiple choice. It's going to be, I hope to do it like Eisgage 100. You know, this game where you have everybody standing and then you give answers, and then you sit down when you get an answer wrong. I have to tell you, I have no way to know in the system who actually got it right and wrong, so I will have to trust you. But usually it works well. And then basically the last person standing is the winner. So the more you are, the more interesting it is, because if there's not so many of you, then of course after just a few questions, the game may already end. Yes, so thank you very much. Enjoy your exercise session with Monty Hall. It's really exciting, Bayesian models, what you can do. It's amazing. And see you next week at 9:15, the usual time for this very last lecture of the semester. If you have any questions, anything you don't understand, fire an email. If you want me to address questions next week, send emails with the questions so we have time to investigate. Yeah? So have a nice day. Thank you.